Signal detection theory is the quantified result of a person's response to a signal with noise present. Signal detection theory uses visual and auditory senses. The two aspects of signal detection theory are criterion and sensitivity. Criterion is the responder's internal threshold that helps determine their response to the stimulus. If the person's internal response is above the criterion, the responder will give one answer, such as, "No, I did not hear or see that." If the person's internal response is below the criterion, the responder will give another answer, such as, "Yes, I did hear or see that." There are 4 types of criterion-based responses: hit, miss, false alarm, and correct rejection. In order for a responder to have a hit, the stimulus must be present and the responder must say, "Yes, the stimulus was present." In order to achieve a miss, the stimulus must also be present, but the responder must say, "No, the stimulus was not present." To achieve a false alarm, the stimulus must be absent, and the responder must say, "Yes, the stimulus was present." Finally, to achieve a correct rejection, the stimulus must be absent, and the responder must say, "No, the stimulus was not present." These graphs before you show the curvature of the 4 possible responses just explained. The second aspect of signal detection theory is sensitivity. Sensitivity is the numerical representation of the proficiency of detecting the presence or absence of a stimulus. The formula to calculate sensitivity, or D prime, is shown below. Here you see the graphs that depict the 3 levels of sensitivity: none, medium, and high. Here are 2 videos exemplifying how signal detection theory is present in our daily lives.
Hey, did you hear that bald eagle?
Bald eagle. I didn't hear anything.
I could have sworn I heard a bald eagle. Huh? Is that in the tree?
I don't see anything.
It's a false alarm.
Is that your phone alarm going off?
Is it? I can't hear it. Oh, it is.
That's a hit.
In a study done in 2015 by researchers at UMass Amherst, titled "The Effect of Emotional State on Visual Detection, a Signal Detection Analysis," researchers wanted to see, does emotional state have an effect on visual detection? They used 122 undergrad students and asked them to find, in Experiment 1, a face through static on the TV, or, in Experiment 2, a house through static on the TV. Of these 122 students, 44 were anxious, 39 were angry, and 39 were calm. Specific emotions were evoked by having participants bring up memories specific to that emotion. By running a number of trials in detecting faces or houses on the TV, it was found that angry emotions were not any different in detecting faces than calm emotions were. However, those who were anxious had more hits and false alarms than angry and calm people when detecting a face through the noise. Implication from these results of the anxious participants might be due to a threat response. Being able to detect a face may have been useful for survival if an attack on the person might happen. In times of evolution, detecting a face through the bushes may have been useful to survive to detect possible predators. It should also be noted that no differences were found between the emotional states when detecting a house through the static on the screen.
In the study applying signal detection theory to the study of observer accuracy and bias in behavioral assessment, the researchers at the University of Houston wanted to analyze the feasibility and utility of a laboratory model for examining observer accuracy within the framework of signal detection theory with regards to aggression. The purpose of this study was to test a procedure for evaluating factors that may influence observer accuracy and bias in behavioral assessment. They hypothesized that hits and false alarms would increase when observers were given brief feedback and told they would receive points for each hit. Hits and false alarms would decrease when observers were given brief feedback and told they would lose points for each false alarm. That changes in hits and false alarms would be more likely to occur within samples designated as ambiguous rather than clear. The participants in this study consisted of 24 individuals. The mean age of the participants was 30 years old. There were 3 video conditions that were 5 minutes long each, and each of these conditions showed an interaction between a teacher and a student doing tasks. Each segment contained 6 clear examples of aggression, 6 ambiguous samples of aggression, 6 clear non-examples of aggression, and 6 ambiguous non-examples of aggression. All the participants were exposed to condition A, the baseline condition. Participants were then randomly assigned to either condition B, social consequences, or condition C, information about expected behavior change, in the second scoring, and to the remaining condition in the third scoring. The 3 video segments were assigned randomly to each condition across participants. Participants received a brief feedback between each of the scoring sessions. The first video condition, condition A, the baseline. Prior to the start of the video segment, participants were told to score as accurately as they could. Prior to condition B, social consequences, participants were told, quote, "When downloading your data record, I noticed that there was not as many aggressions scored as there should have been. It is really important that you score all the aggression that occurs and that you try harder on your next video," end quote. And prior to condition C, information about expected behavior change, participants were told, "These clips resemble the actual person's behavior on a day when more aggression because the behavior change intervention was not implemented." After the participants completed their tasks, the number of hits and false alarms in conditions B and C was then subtracted from the number of hits and false alarms in condition A. The change in hits and false alarms in each condition was examined for each participant to determine the number of participants who showed evidence of response bias, the number of participants who showed an increase in sensitivity, and the number of participants who showed a decrease in sensitivity. These results were examined separately for each participant for the 2 groups of participants who were exposed into the 2 conditions in a different order. The latter analysis was conducted in order to identify possible sequence effects. Data for the 12 participants who experienced condition B prior to condition C are displayed on the left, and data for the 12 participants who experienced condition C prior to condition B are displayed on the right. Under condition B, 12 of the 24 participants showed an increase in both hits and false alarms, indicating that social consequences bias responding. 1 participant showed a decrease in hits and false alarms, an outcome that is consistent with response bias but opposite to the direction expected. An additional 5 participants showed an increase in false alarms only or an increase in false alarms combined with a decrease in hits. These patterns suggest a decrease in sensitivity. For the remaining 6 participants, outcomes suggested an increase in sensitivity, with 3 participants showing an increase in hits only, 1 participant showing a decrease in false alarms only, and 2 participants showing a decrease in false alarms combined with an increase in hits. Similar results were obtained regardless of whether the participant was exposed to condition B before or after condition C. When exposed to condition C, 5 of the 24 participants showed an increase in both hits and false alarms. These 5 participants had been exposed to condition B before condition C and had shown evidence of bias under condition B. Among the 12 participants who were exposed to condition C before condition B, no showed evidence of bias. 3 participants showed no change in responding, and 2 participants showed evidence of response bias but opposite of the direction expected. The remaining response patterns were similar to those of the participants who had experienced condition B prior to condition C. Together, these results show that social consequences, but not information about expected behavior change, altered response bias among some observers who were scoring clear, ambiguous events in laboratory setting. Sequence or interaction effects also appeared to influence the outcomes for observers who were exposed to the social consequences. That is, effects of social consequences either carried over into the next scoring session or altered participants' responses to the experimenter's statement about expected behavior change. The purpose of these experimental arrangements was to advance basic and applied research on observer accuracy. A similar procedure may be useful for evaluating other variables that may increase response bias or alter observer sensitivity. These factors include the probability of the behavior, type of instructions of training provided to observers, and the availability of concurrent consequences for the various response options. Research findings may lead to greater understanding of observer behavior and thus ways to improve and performance of those who collect data in the field.
Thank you for watching our video. We hope you learned a lot about signal detection theory.